I want to say thank you all for taking time out of your busy schedules. I see people from all different time zones on here today. And so I want to say before we even start that for those of you I know, for instance, Singapore and Indonesia and a couple of you others, it's in the middle of the night or very late for you. And we are recording this and it will be available to you again after. So if for some reason you can't make it through the whole thing, please not to worry. We will send out an email from Proengin with the link to the video so you can still get access to it. My name is Christina Baxter and I own a company called Emergency Response Tips. And we do a lot of work with developing new technologies and training and consulting with manufacturers to make their products more operationally relevant to us in the field. And this series of workshops and webinars is sponsored by Proengin, and they are one of our partners in this program. So I want to turn it over to Scott to say hello, and then we'll start in.
Good morning, everyone, or wherever you are, evening or night. So I'm Scott Hartley. I'm the CEO of Proengin, Inc. So we're kind of really excited about this topic today because I think it's a really pertinent one and one in the industry. I think, the combination of detection and decon put together is not always talked very much on, and it really involves the combination of both put together. So hopefully this will be very pertinent and helpful and educational to the audience today.
And before we get going, I also want to say a thank you to First Line Technology out of Virginia. And they, as you see some of the videos that we put together for this course to show you some of the principles, we actually worked with First Line in their laboratory to do those. And they have been nothing short of wonderful in helping us get this information across. So you'll see at the end of some of the videos, it'll actually have a thank you to them as well. And while they're not listed as one of the sponsors of this, they surely have done a lot of heavy lifting to get us where we are. I'm going to turn off my video and just go to voice so that your focus is on the screens. Please note that there is a questions area. So if you do have questions, I'll be trying to watch them as much as I can throughout, but we will get to questions at the end. So let me take off the video and stop sharing you with my mugshot. And we'll go on to just being on the screen. So hopefully everybody can see this well. And we are going to talk about detection, decon, and verification. We're not going to spend a huge amount of time on the overall detection process of a scene, because really what we're trying to talk about here is the important part, the role that detection plays in verifying that your decontamination process was efficient and effective. So a couple of different slides here that I stole from First Line. And really what it is here is just reminding everybody that in the last 100 years, there have been so many changes in updates to the science behind skin permeation and permeation in general in different materials. Yet we're still doing a lot of the same things. So I like to call these 100 years of decon history unimpeded by progress. Because why are we doing the same things when we know so much more today? And the same thing when we get into technical decon. We're still following the same process we followed during World War I. And in many cases, this is slowing us down and providing little, if any, benefit. And in some cases, more harm. So when we get into some of this decon, you're going to see the process we follow, whether we're doing air-based, whether we're doing a hybrid decon, or water-based. And what we want to know is, before you leave this webinar, that you understand when do you apply which type of process. Is it purely a dry decon that you need? Or do you need a purely wet decon? Or is it somewhere in between? And so as we start going down this road, I just want to make sure that everybody's on the same page, that we really have so much more today to work with. So starting out with the hybrid decon approach, reality is the US military started following the hybrid decon approach in 1931. So it's nothing new, it's just talked about more. So in 1931 was when the military started looking at Fuller's Earth. as a method for trying to absorb up a lot of the different materials. So it was kind of an absorption in some ways and adsorption in others. Now, fast forward to the 1980s, and you ended up with the M291 kit. And that was the first time that the US government went between a woven fiber with other material impregnated within it. And that was to get absorption and adsorption in the same thing. So ab with a B and ad with a D. And so the M291 kit was the first attempt. And it worked quite well for what it had. Now, for those of you who remember wearing it and working with it, it was quite messy. And this material, while impregnated resin inside, the black charcoal residue went everywhere. And so you really ended up having this all over you. In terms of absorbent materials, the FiberTech was developed in 2000. And reality is that was following a series of different experiments by the Department of Defense, where they evaluated a whole slew of different materials to find out what was the most absorbent, and then a whole nother series of materials to find the most adsorbent. And then they put those together, and FiberTech was born. Texas Tech had produced the most absorbent cotton that we had ever found. And from there, that's where the product became. Now, that's not the only product out there, but that's kind of the history of the one that we're going to show you today. Now, in terms of the process that we follow, many of us still follow that EPA 9-step, some of it use like a 19-step, but it's a EPA process that was out there that was released in one of their field operating procedures. Reality was it was released in 1986, and it was designed for the use at a static site. And so it was a system that they had set up and were leaving set up. We all adopted it into the emergency response community. I know that my time in the fire service, we always used the 3 kiddie pools and did our business. It wasn't until the late 90s, early 2000s, when we started looking at more expedient decon procedures and started really evaluating what really needed to be done here. And for instance, it was not until 2007 that we started our project looking at skin. And in that case, we partnered up with South Australia and the Australian government and started figuring out how did the chemicals interact with the skin level? How high of a concentration did they have to get to start that interaction? And was washing it off actually helping or hindering? And so in many cases, we found that an air-based decon was much more effective than ever adding water. And in many cases, if a material was not water soluble, adding soap pushed it through the skin. And so by increasing its solubility, and you had something against skin, you actually started pushing it through. And so we had to start going back and figure out, where are we really? So let's just look at decon as a whole for a moment. So in terms of the primary purpose of decon, it's really about preventing the spread of contaminants, reducing that contamination level, and preventing that possible secondary exposure. Now, we also always have that secondary mission where you're often the first person talking to victims, and that allows you to start gathering some good intelligence information of things that were downrange. But reality is, decontamination is no more than a physical or chemical process that's reducing. And this is important here when we talk about reducing, because we're not completely eliminating the threat. And we're going to show you that in terms of detection. And how do we get it down to a point at which we can say that we think somebody is suitably clean? So we're going to reduce and prevent the spread. And then we could also remove or destroy the material. We very rarely do the destruction on a human because that does generally involve heat and other things. So just remember, there's the physical removal, which is just capturing or moving the contaminant. And then there's the destruction, which is fundamentally changing the material to a less hazardous or no longer hazardous. And this is important because oftentimes you're destroying the material and it becomes less hazardous, but it's still a hazard. So we have to wash off afterwards or different things to make sure that we minimize that total contact time and exposure to us as the operators. So just a note on decon principles. When you're starting to look at all these things, you need to decon as far forward as possible. So try to limit that spread of contamination and make sure that any gross contamination stays downrange. You can't wait until a decon line is ready if something has happened to start removal of the contamination. And what I mean by that is, if you're the first arriving unit and are coming onto a hazmat event, and you're not part of a hazmat team, it is still your responsibility to try to minimize that contamination. And that may be as simple as having them remove the outer layer of clothing and getting 90% of that contamination off of them. We also want to decon only what's necessary. So we don't want to just spray the whole body if there's only a small area that was contaminated, because that actually increases the surface area that's in contact with the chemical and can create more of a problem. So we also want to limit the resources and minimize the waste. Decon by priority. So those people that have been in contact the longest, because time is really of essence here, get those people out. Or if we're talking about a responder, is there somebody who's low on air that has to get out quickly? Is there somebody who has gone down with some other type of injury that you need to do a cutout? Those types of things are going to be situation dependent. And then decon as soon as possible. I'm not teaching a whole decon course here, so I'm not going to go into the timelines that are critical here, but please do not let surface contamination get into a matrix. That can be as simple as having it on skin and getting into the skin matrix, making it difficult to remove, or it could be getting into different materials like your sensors. So if you have one of those rubber casings on the outside of your sensor and you leave a contaminant on there longer, the chance of it getting and becoming permanently embedded into that housing is oftentimes time dependent. So this chart here is meant to just give you kind of a first thing to do, and this is meant for emergency decon. These are for the first person on scene. This is not necessarily for the first hazmat on scene, because oftentimes the first emergency responder on scene is not necessarily trained above hazmat operations. So in this case, we try to keep it simple. And so if we have this divided out by a gas or vapor, a liquid, or a solid, and then we have no symptoms of exposure, minor signs and symptoms, or serious signs and symptoms. And then we go through and start looking at this. The only time that we start using large amounts of water is when we get down to that serious signs and symptoms. In often cases, that's going to be corrosive materials and things of that nature. If it's just a standard gas or vapor and they're not showing signs or symptoms of an exposure, remember, these people are not wearing respiratory protection. It's going to affect their lungs far before anything else. Those people, we just move to fresh air, and if we have a fan available, put it on them. If it's a liquid, we generally remove that outer layer of clothing. If they're having a little bit of sensitization to the skin, you may spot wash that area, but again, not spreading it. And then for solids, especially those powdery particulates that like to go airborne, we'll oftentimes try to gently wet those down on the outer layer of clothing and then remove the clothing. The reason that we do this is as you start to pull the clothing over somebody's head or you start to move it, we don't want to aerosolize particulates and make them something that, again, if these people are not wearing respiratory protection, we don't want to make it worse. And of course, the serious signs and symptoms, it's all about getting the clothing off, enhancing ventilation, flushing eyes if it's a gas. And if it's a liquid or a solid, you may have to go into high level flushing. Now, to actually explain some of these, I want to have Scott show you a couple of the videos that we captured. First, we'll show you how to use the AP4C to measure these, because that's the detector we were using, and you'll see at the end why we had to use that one only. But reality is, I want you to see how a gas or a vapor, a liquid, and a solid get into material and then come off of material. So when you see these videos, I just want to note that the material that's used is from an urban search and rescue garment. So it's a multi-layer garment that has going to be exposed to the different chemicals. So Scott, I'm going to turn it over to you to go into some of these videos.
Okay, thanks, Christina. So first I'm going to go over the AP4C. So the AP4C is based upon flame spectroscopy or atomic emissions spectroscopy, if you're familiar with that. So in the case of what we're doing is we operate on a similar principle to how fireworks operate, in the fact that certain materials give us a unique response specific to that material and that material only. So what happens is an incoming airstream is we use a flame, in this case, to excite the materials. And what happens when the materials are excited is they produce certain wavelengths of light specific to that element and that element only, and that allows us to operate. So what we're seeing here is the insides of the detector. This pre-chamber ahead of where the flame is meant to keep any flammable materials that might be ignited from the flame from going outside. So it kind of acts like a silencer on a weapon, for example, so no flame or will get outside of the thing. So what we're seeing is the airstream being pulled through. It's exposed to the hydrogen flame. And then inside the detector are a series of lenses and a CMOS sensor. So what we're doing is constantly capturing the light that's produced and then analyzing it and looking for the fingerprint of certain elements that were of interest to be able to do there. So now we're just looking down on that, showing the CMOS sensor. So part of the science of how the device works is the ability, the algorithms inside the CMOS detector that allow us to use solid state electronics and take advantage of that capability to be able to do there. Now, since you're operating on the principle of light versus in some other technologies, you're looking at electrons or a response of a spectral over thousands of wavelengths of light, what we're really focusing in is on the visible light. So a way of looking at this is we're doing truncated spectroscopy. So you get the accuracy of a spectroscopy machine, but you're doing it real time, multiple times a second, and you're getting summary data every 2 seconds. So what we'll be showing in the next couple slides is kind of one of the reasons why this is a great tool to utilize in these scenarios, is that it's a very fast responding time. So every 2 seconds, it's telling you what went through the detector the last 2 seconds. So that's important when you're trying to go over a person to validate it, or something that's gone through the process of decontamination to validate it. It's also very sensitive. So when you're talking about light and specific wavelengths, the presence of those light allows us to be able to differentiate at really, really low concentrations, which is another important aspect, which we'll talk a little bit more further from that. So as what Christina talked about is we're going to go a couple examples. So first we're doing ammonium. So ammonium is lighter than air. And so what we have here is the ammonium is in a dish underneath the protective equipment. So you can kind of see right there just a little bit of the peak of that. And we'll just show you what will be sticking out the detector coming up just in a little bit and sticking under there. And you can see that the detector will respond fairly quickly. So ammonia being an H3, H3N, will respond fairly quickly. It'll have to be on the H and O channel to be able to see there. So it's a colorless gas, it's fast evaporating, and it's lighter than air. So you're kind of seeing the response there. So what we're doing is we're showing on top of the material. So you're seeing the ammonium is able to permeate through the protective equipment in this environment to be able to do there. So as you know, you need to select, especially based on the concentration of the ammonium, the right protective equipment. Ammonia is a very small molecule, so seams and other things like that can permeate through there. And so you need to understand your breakthrough times, especially on the concentration of the material you're dealing with. But once we stop exposing it to the material, we lay it out, you can see that it's off-gassing fairly quickly. So the important consideration here is a lot of air will be, pushing air, fans, ventilation will help drive off that material quickly. And then you get the advantage of the fact that it's lighter than air. So it wants to, readily get out of there as possible. The next example is another vapor we're doing, but in this case, we're looking at hydrogen sulfide. So hydrogen sulfide in this case is heavier than air. So what's going to happen is you're going to see the response. So first we're dealing with the creation of the hydrogen sulfide. See there is some color associated with it to be able to do that. And so what we're doing is we're applying the protective material on top of it. And then we've gone through a couple minutes of the exposure, and you can kind of see there. So at first you get 5 bars of response. So that's kind of equating to around 1.9 to 3.8 parts per million. And then it slowly is working its way down the chain for that. But the significant exposure level for that, as far as the military, for a 10-minute exposure is 0.6 ppm. So we are above that in this level. In a severe case would be 30 ppm. Now, of course, this is on the outside of the material, right? It's not what went through the material, but just to be cognizant, that is on the outside of the material. As you know, hydrogen sulfide smells like rotten eggs. And if at high enough concentration, our noses actually can have what's called odor paralysis, and you can stop not smelling it anymore. So that's another consideration when you're exposed to it, and it can ignite and exposed with it. But in this case, similar to ammonium, how we mitigate that is we want ventilation and take advantage of that. But in this case, from a detection standpoint, a lot of times when we have a source of materials, we're always sampling above that source. In this case, because it's heavier than air, we need to be sampling below the surface in order to be able to detect it as much as possible.
And Scott, I want to jump in here just for a second and just make sure everybody saw it when we were out here and saw the material coming back off of it. So we had the higher concentration, and just letting this in air, albeit it takes a lot longer than it does for ammonia, the SO2 or H2S, whichever one at the time we were producing, is coming off on its own. If you had the fan to increase it, you'd be able to remove that right back off of there and much quicker. And so this is when we talk about a fan-based decon, any of these types of materials that are gas phase that are not being interacted with water will allow us to get that off of the gear relatively quickly, and much better than if we actually did a water-based decon. So those ones were just gases. And so we just wanted to show you the gas comes on, and those lighter than air gases come off rapidly. The gas comes on, and the heavier than air gases come off a little bit slower, but still rapidly enough that it's usually gone prior to you even getting them through a decon line. So if you were to put a fan at the front of your decon line, you would have a complete decon much faster than any other way. Now we're going to get into some solids and liquids, and these generally require that we do a hybrid approach, which means we're not going to use high flow water and go into a water-based approach, and we're not going to just use the air-based approach. So the first thing we look at is say, did a chemical exposure even occur? And if yes, is it interacting at the skin level? What we're looking for here is somebody saying that they have pain. We may not see anything. Some of the blister agents, obviously, we don't see the blister, but they do feel the pain pretty quickly. Irritation or redness or any dermatitis-like symptoms. And if they have any of those, then we're going to follow the hybrid approach, which is blot, apply, remove. So we call it the bar method. So blot any residual chemical. So if you can see any chemical there, whether it's a solid or a liquid, go ahead and blot that material. By blot, I do not mean white. Blot is hold the material against the skin or against the PPE and allow it to naturally move to the more absorbent material, which is going to be whatever type of absorbent we're using. And so we don't want to wipe right away, because by wiping, we actually increase the surface area of the contamination. And it also implies that we're applying some type of pressure. And we don't want to push the material into the skin. We want to let the absorbent do its job and have it go from one area to another that's more absorbent. After we've done that blot, in the area of concern, not the whole body, we apply water, soap and water, or an appropriate decontaminant. And the reason I say appropriate decontaminant, if we're talking about skin, that may be something like RSDL, reactive skin decon lotion. If it's water, let's say it's chlorine. If chlorine gas had gotten on the skin and started to interact, We may blot any area where we might see any type of interaction there. And then we might just use water. Because if we use soap and water, we're going to increase the solubility of chlorine at the skin level. And so we're going to stick to just water. If it were ammonia, we could use water or soap and water. And as we start getting more into the different liquids and things, then we still have to start thinking that way. And at the end, we remove any residual soap or decontaminant. And what we mean here is if you used a strong soap to try to encapsulate the material or pull it away, or if you used a decontaminant like RSDL, you need to remove that so that you don't get skin sensitization from the soap or the decontaminant itself. So the last thing we want to do is cause harm to the skin from the solution that we're doing. So all of these things need to be taken into consideration, but just remember, it's always bar, so raise the bar for decon, or blot, apply, remove. So we're going to have Scott walk you through two more that we did. And the first one is fentanyl, with the exception of this large bulk right here, which is Tylenol, just to show the same thing, because we did not want to have larger amounts of fentanyl just floating around in the space. So I'll pass this back over to Scott and let him walk you through this one.
So in this case, we're dealing with your white powder call and dangerous material. So Tylenol is an opioid, so it falls in the same opioid class. But as a powder, in a powder form, most likely it can be aerosolized. Most times it wants to go down. It's heavier than air a lot of times with those powders, but they can be agitated and be in the air. So the AP4C is able to detect aerosolized materials, but in this case, it most likely won't be, and it's in this scenario, it's as a powder. So because it's in its powder form, what we have to do is introduce heat in order to be able to detect it. So what we're doing is increasing the vapor pressure, releasing more of the atoms, allowing the detectors to be able to see that. Same thing with if it was other technology, you're adding thermal to it in order to release more of those materials and be able to do that. But just to be cognizant, the more threat to us as humans is aerosolized. When you're dealing with opioids, is aerosolized getting into your respiratory system. It's a less of a threat through your skin. It takes a longer time unless you have a cut or you help facilitate it using hand sanitizer or other things like that. So what we're going to do is we're going to show the process of heating it. So we're going to take a sample. So the AP4C comes with the S4PE. We recently released the S4PF. So the S4PF, the advantage of that is it's been redesigned. So the scrapers are better designed to pick up powders, and they have much higher temperature profile. So when you're dealing with pure fentanyls, much higher melting temperature. So in that case, the device can go up to around 540 degrees Fahrenheit versus around 340 for the S4PE. So you need to be cognizant of what the material is and making sure that you're introducing enough heat to vaporize it and to release enough of those atoms that you can detect it. So in this case, you're going to see that. It's going to show up on the HNO channel to be able to do that. You'll see that really quick. So the blinking light means that it's coming up to temperature. An additional feature of the S4PF is there's a longer ramp up. And so with opioids in particular, you can actually caramelize them or change the structure. So you need to heat it more slowly. So now we're starting the decon process. So as Christina was talking about, we first want to blot the material. As we're going through that, you can kind of go to that and we can walk through that process right now to go in the video there. It's not wanting to, there we go. So we're starting to so we're wetting the fiber tack. We're trying to get up as much of that material in the bulk form as possible. Now, even though that material has been cleaned off the surface, there's likely still some residual. So what we're demonstrating to you is that you can still do that. So this is using the S4PE new scraper, clean scraper, because if you're using the other one that had stuff on it, you're still going to get a hit most likely. And so again, we're introducing the heat to it, and we're going to get a response on the detector with it. Now, since there's less material there, it will get a lower response as far as some of the levels on the detector, and it may take a little bit longer to be able to do that just because there's less. But this is something that you have blotted it. Now you have reduced a lot of materials on there, but there's still some residual. So now we're starting to apply the hybrid decon. We're applying the Dahlgren decon solution that's been mixed and spraying it onto the device, and then now giving some time to allow it to work. So we're doing it for 5 minutes, allowing to sit as required by the manufacturer. thumbs up with the time, contact for the 5 minutes. And now we're, after the exposure to it, we're removing the material. So we're rinsing the solution on the material to further clean it and to remove the dogrin that's on there. And as you see, we're collecting it into, and it's important that we collect that material, and we'll show you a little bit why in just a second. So we've blotted that material away. And so the fentanyl has been degraded, but it's still, there still is some capability for us to detect it into the solution. And we're showing you here. So again, taking a sample out of that solution that's been wiped off, we're introducing heat, and you're getting a response on there. So we were talking about 2 bars, it's around a concentration of 7 to 23 parts per million. 3 bars will be in a range of 23 to 63 parts per million in there. So definitely not something you would want to inhale at those concentrations, but in this case, because it is in powder form, not being aerosolized, and then we're introducing the heat into the system, we're still able to detect it and tell you that it's present there. But it's much less of a threat to us now that it's been fully deconned.
And one of the things that I wanted to add there, and is important, is because we're detecting, not identifying, we can see the degradation products in the washed water. And so we're seeing that nitrogen moved from the soup material into the decon wash. And then when we tested the soup material, we tested it about 4 different times trying to get some measurement, and literally had no measurements on the soup material at all. So we were able to move it from one area to another area, and now we can safely come out of that soup.
So the next material we're going to do is malathion. So malathion is an organophosphate. So this would be a surrogate for your nerve agents, which are mostly all organophosphate-based materials. Now we chose malathion because it's less harmful to us as humans. With it, it's not very harmful. And then there is a sulfur agent or vomiting agent added to it. But what you're seeing here is we put 3 little dabs of it onto the material. Now, most organophosphates, they have very, very low vapor pressure, so they don't release many atoms to be detected. But if you have enough sensitivity, in this case, the AP4C can get down to 2 parts per billion, B as in billion. If you hold it and over the conditions, you should be able to detect it. And this is what you'll see when we start to run the thing. It'll take a little bit longer because we're right out the single parts per billion concentration, but these materials will off gas. And this is not just present with their malathion, it's also present with your B series agents and even your A series agents to be able to do there. So provided it's not super, super cold out, you should be able to off gas enough of those materials at room temperature to still detect it, even for those V and A series agents to be able to do that. So what you're seeing is a single bar. So you're talking about around 2 up to around 7 parts per billion. The 2 will give you up to about 19 parts per billion is the concentration we're seeing in the device with there. So each of those are off gassing. So when you're doing it, you want to be downwind, sampling for it, get as close to the surface but not touching it, and being able to detect it. If you aren't able to originally detect it, you could use headspace. So now what we're seeing is the first part of the bar method. We're blotting it. So we're trying to get most of that bulk material off the surface as possible. So we're putting in contact, we're applying some pressure, we're allowing that material to soak up into the thing. And what you're seeing is you're rotating it, and now you're gonna try to remove something. So you're going from the adsorption to adsorption. So now you're trying to wipe that on there. Now, one thing to notice there is what you're basically doing is you've taken up a lot of that bulk material. What you may see out of the right in the beginning, if you were to do this, because you increase the surface area of that, you might get a little bit of a higher concentration immediately. Now there's less material there by far, but because you increase the surface area, it could vaporize off a little bit. You can get a fairly fast response. So you're using the physics to help you. Instead of being in a small area, you're increasing the surface area that allows more of it to off gas with it. So now we're seeing again applying the hybrid decon process. So we're covering all of the surface area with that, allowing the process to go through and start to break down the key parts of the chemistry associated with it. Waiting that 5 minutes. and now trying to detect the material. So a lot of that material has been reduced. We have it covered, and so you're seeing there's no response getting from the detector. So there's no organophosphates that we're seeing coming through there with it. So it's successfully done what we're trying to accomplish with the material.
And this one's really important to me because it represents the G and V and A series agents. So when we did the malathion, it was intentional as a far less toxic surrogate for organophosphate threats. And you can see that reality is the Dahlgren Decon destroys those organophosphates very quickly. Now, had we gone and captured all of the runoff, like completely rinsed this off, we would have been able to find some phosphorus. And that would be intentional because we wanted to get any of those breakdowns in the solution. So let me see if I can get this to keep going.
Yep.
And sorry, folks, my video editing is not very high.
So this is another important aspect to talk a little bit further with it. So the actual Dahlgren decon material in itself does have phosphoric acid in it. So that contains phosphorus. So when it's first being mixed, before the oxidizing part of Dahlgren decon can kind of take over and reduce that phosphoric acid, you will get a response. So this is one of the important aspects of understanding decon and detection as a system associated with it. So if you're doing organophosphate and you're doing the solution when it's first in its active phase, you very well could get a response because of the phosphoric acid that's present in there. Now you're trying to do organophosphate, right? So you could say, oh, I still have some of the material there, but it's the actual Dahlgren, not the material. Now that material, that byproduct will, the ability to detect that kind of goes away, but it's an understanding of the system and how the decon system actually works and what the chemistry of the decon system contains. And those two things need to be taken into consideration to develop your processes. So again, it's one of the important aspects of understanding your decon solution, understanding your detection solution, and understanding the interface between the two of those to be able to do. So in this case, if you're dealing with like a fentanyl and you see the phosphorus channel, that should be expected, right? But if you're doing organophosphate, you have to be trained to just understand at that low concentration. You may see it at the beginning parts of the process when that mixture is being occurred. So to just be aware of that as part of your training solution in appropriately respond accordingly into that.
Okay, so what I wanted to show you is my take on where do we apply each of these different methods. And so I know this is kind of a big eye chart, but when we talk about gases and any of those toxic and corrosive gases, if they're not interacting with the skin, if you're not seeing interaction with the skin, then we just use a fan. Anything for explosives, radioactives, flammable gases and solids, any of those types of things, we just use the blot. So we use a dry base decon. We don't do the entire blot, apply, remove method. We do the bar method or the blot, apply, remove for any poisons, biological warfare agents, chemical warfare agents, and drugs. And then we reserve our wet decon for corrosive materials and oxidizers. And so when we use wet decon as our solution today, we use high flow wet decon. So none of this misting type of material anymore or low flow tents and things. It's very much a high flow hose stream with corrosives and oxidizers, and for a period of time to make sure we get that material off of their skin. All of the others, we use either a fan, a dry, a bar. Sometimes we use a bio when it's certain things that fall under the EPA regulations. Then we go to wet. And obviously there's the outliers like mercury where we do other things. You know, in this case, we might be using a sulfur-based shampoo to bind the mercury to the sulfur so that it doesn't go airborne anymore. And so each of these things allows us to look quickly across the spectrum of materials and figure out what you should do. If you want to get into more detail, and I didn't put this in here, but thank you, Rick Emery, for reminding me. You could go into the Emergency Response Decision Support System, or ERDSS, which you can access at chemicalcompanion.org, and that will allow you to walk through for any given chemical and figure out what is the most appropriate decon method based upon the concentration and the time in contact, whether it be for people or for objects. And so that will bring you into a more detailed approach, but this is kind of my cheat sheet.
Yeah. And then Christine, build on that, as well as once you're in the ERDSS, the AP4C or other detectors are in that. So it allow you to, it provides information on both TLB and IDLH. And in the case of the AP4C, it'll show you the bar levels as how it correlates with those. It also help you if you're, for example, using a PID to understand cross sensitivity with other materials in there. So if you're getting a response, so it also ties in the detection component with the decon component together.
Yes, exactly. Now, in terms of the decon layout, how have we changed and modified what we do based upon what happens today? Now, this is where you're going to see that I'm a combination of old school and new science. And the reason I say old school is I'm old. Okay, so these tables that you see here throughout, I like to have tables that are wrapped with visqueen ahead of time. And so that way I don't have to try to reach down and try to find stuff. So usually when I'm setting up a decon system, if it's a wet decon layout, I always have a fan up front just in case. We have some different lights and things on scene, generally battery operated, which again, it may bring us back to doing a lithium battery call later. But I have a table here wrapped with visqueen, and that way I have things to tape stuff to. Because if I'm using any type of white, whether it be FiberTac or something else, I like to have them open before I need them. And so get them open and then use something like chem tape to tape them to the table. Then you're just reaching over and grabbing the one you need versus trying to fight with getting it opened when you're in a hurry or somebody may be in a quicker type of thing. Also, usually put the trash bag taped right there to the table. That way I can start taking the materials afterwards and throw them in there. The containment pool is still something that we're capturing the water in, and then use a sump pump to pump it right into an overpack drum. And that way you literally have a continuous flow and you're not standing in liquid that will build up and provide you more contamination. Also, remember if you're going to use a brush in decon that you need a brush with very soft bristles. I know years ago we used to use some of those with hard bristles, but we found over the years that those hard bristles actually degrade the protective material that you might be scrubbing. And so we have to be very careful to not push material in we're trying to remove it from. Now, the next thing we get to is another table where we start doffing our PPE. This, number one, can be used for balance, but it also allows us to quickly and easily get our material into trash bags and out of there. The most important thing also, and that I think a lot of people seem to forget, is that there needs to be a rehydration and a hygiene effect at the very end. I know we're going to have rehab set up, but that hygiene step is critical to do early and often. And the reason here is to ensure that if anything were to get on the skin from the decon process, that it gets removed immediately so that we minimize that time on target and minimize the amount that gets through. I'm also a stickler about making sure at the very end of the decon line, before anybody steps out of the area, they have some type of footwear back on their feet, because you don't know what happened on that scene before you arrived. We make assumptions when we get there based upon observables. But what if somebody had driven through the residue and you didn't notice that? And now you have somebody stepping off into a material that is toxic. We don't want that to happen. So we always have to have some type of footwear at the very end. And you can see as people have come out and they've done hygiene and doctor PPE, we need to make sure that we detect that they are clean or lower than we can measure before we allow them to move out of this warm zone area. Now, if you were doing a hybrid decon, you can use the same layout. But what you end up doing here is instead of having a pool with liquid going into it, you just have some type of absorbent here. And when you apply your decon solution, we usually use an electrostatic sprayer that's sitting here on the table. You literally just spray it. You don't have a lot of overspray. Anything that comes off gets in the absorbent pad, so you don't need your sump pump. You don't need your overpack. And reality is you're just going to throw this material into a trash bag just like you would any other type of material, like your PPE if you're using disposable. And the same process occurs as you come through. You do your hygiene step, and you also make sure everybody has footwear before they step out of that warm zone area. And again, detection is critical. But as you look at these layouts, I try to keep everything laid out in the same way so that you have that muscle memory. And if you have at least a hybrid decon set up, usually what I do is have some type of fan. If you have a battery operated one, nice and easy to have here, have a charged line here. Because if somebody does have a corrosive or an oxidizer on them, I want to have a charged line ready to go to get them high flow water across that skin surface to ensure that we minimize the damage. And so these are kind of a more modernized approach to that same layout so that you're taking baby steps before we go there. Now, Scott, do you want to cover this one?
Yeah, sure, I can do that. So in relation to monitoring materials, one of the key aspects, there's two key things when it comes to monitoring of detection or validation of detection once you've done decon, and that's response time and sensitivity. So if the detection is being done, the decontamination, is being done properly, you aren't going to have much material there. Ideally, you won't have any material there, but you have to understand your detector that you're utilizing, or multiple detectors you're utilizing, how quickly they're going to respond, and then are they at sufficient sensitivity or levels of detection that they can detect it, especially depending upon the material, and then what the TLVs of that material are, or IDLHs in some cases can be really, really low, especially if you're talking about nerve agents. So from that standpoint, the AP4C is a good option to utilize, just because it's a very fast responding and its levels of detection can be very low. PIDs can also be utilized, but you have to understand that as you're getting down to lower and low concentrations, it may not be sensitive enough, or it may take an extended period of time to be able to do that. And I think we have a video a little bit later on there. An additional aspect of that is radiation. So when you're talking about decon, you could be deconning from a radiation scenario, so you need to actually be able to monitor to that. And then also your pH papers can be utilized to assist with that. But again, if you're dealing with a very small amount of material and you're looking for a response on that paper, you just must be cognizant that you may not necessarily get much associated with that. So you just have to be careful. But kind of the things you want to be looking for, as far as our eyes are a good tool to be validating some of this, is looking for stains, for corrosive effects, effects on the skins post-decon. That would be indication of something has been exposed to there, so they need to be seeing secondary medical attention to be able to tend for that. And then also from a standpoint of a collection of information or evidence collection, having samples to send to a laboratory for that. Now, one big thing to take in consideration is if you're getting a hit very quickly going post-decon, there is a potential that that's giving you a quick indication that you missed an area. So one of the challenges that you face with sometimes is you have to make sure you're getting thoroughly exposed through all the surfaces. And if you miss the surface and you're getting a quick hit, then that's probably a pretty good indication that you missed an area for that. And so you need to obviously be quick responding to address that concern associated with it, as far as because of the threat profile of that, and then just that it's a high, exposure level on there. But if you are doing it at a low concentration with that, you do need to take into consideration the speed of detection, right? So if you're moving your detector really fast, but your level of detection is 30 seconds, right? To be able to do that, you have to make sure that your movement of your detector over your the area to validate it is correlated with the response time, or else you could get a false sense of security. And that's the thing that you most want to avoid, is thinking that something is safe that's really not. So in this case, slow and steady, and understanding the equipment you're bringing down range is important. And also having more than one detector in technology is not a bad thing to have as well, just because you're getting that that confidence associated with it. But you also need to 100% make sure that whatever you're bringing and using is able to detect. And if you don't do that, and that's obviously a really bad thing to do.
Okay, I'm going to show you this video because I thought it was kind of cool to show here. This is one that Proengin was there, so Scott was there helping us. We had Guardian Center, so Carrie was there, and we had First Line, and so the legs on the right are Carrie, the legs on the left are Corey. So what we were doing is we had a bunch of different sensors, and we were putting them in the hood and using low-level calibration gases and just seeing what type of responses we could get and seeing what types of difference in response we would see. And so I thought it was kind of cool to show this one, just so you could see the difference in how responsive things are. This is not to say that any detector is better than another. It's just to say that there's different uses for different detectors. And so in this case, it's SO2 coming out. And you'll see right away, just going past the AP4C, it went crazy. Okay, so didn't take any time, didn't have to get up close, but none of our other sensors are going off for this. And we do have several SO2 sensors in there. We're looking to show the students cross sensitivity and things. So we're in a double-sided hood here. Now we're going to show to the SO2 sensor and hold it there and have it coming directly on it. And see how long it's taking with that SO2 coming out at constant concentration. Although low, it's still within the detection range of the instrument, and it took quite a while to get there. The response time here is actually a 60 seconds. And so that's why you're taking so much time. 60 seconds is when it takes to be a quantitative number. And so we're going to try down another one here. We're going to get a little bit more sensitivity here and a speed. But again, we're going to have to wait 60 seconds before it's quantitative. And so this is just showing you that I know I drive a lot of people crazy probably with response times, but I always try to remind everybody that just because you have all those sensors on one screen does not mean that you can read the results at the same time. On a standard 4-gas sensor, you have your LEL and your oxygen that's reading at about 15 seconds response time. If you have a PID integrated, that's about 3 seconds. If you have CO, that's going to be about 35 seconds, and your H2S is going to be around 30 seconds. And so trying to think about which one responds where, and God forbid you're trying to do something like SO2 or ammonia, which come out at 60 seconds, or hydrogen cyanide at 200 seconds. Those are the types of things we have to remember. And so when we start moving our sensors very quickly, and where Scott was saying to go low, slow and steady, it's really important that you go slow and steady and you keep in mind that T90 or the response time of the instrument, because that's going to dictate how fast you can move. Now, obviously, on the slower sensors, the things that take 30 seconds and longer, I usually don't use them for post-decon, because at the end of a scene, when we're deconning somebody, they're already tapped out on the amount of work they're going to be doing, and they're ready to come out. And if we're going to say, okay, stand there for 5 minutes while we measure you, they're not going to be, that's not going to be conducive to a good operational environment. So we'll leave it at that. But what I do use those systems for, because they're quantitative, I'll often bring them down range and set them at the areas where we're setting our zones. And that way we can continuously monitor in those zone areas and make sure that we have concentrations that are suitable for what we're doing. So I'll turn this one over to you for a moment.
So as far as the monitoring, it's to kind of hit on what the last point that Christina made, which I think is a really important thing, is where you're setting up your decon line. You want to make sure you're close to the event, but far enough away that there's no residual motion there. Because if you think about it, what you're trying to do is look for really trace amounts post decon to validate that the decon's been done properly. If you have stuff coming down, even though it's coming, or it's in the air and it's going down to your line, you're going to get hits on your detector, but it's not from the decon, post decon, it's from the actual event that's occurring. So that's why it's really important to be monitoring what's coming, because winds can change and other situations can change. But you want to make sure that when you're doing this validation of the decon process, that you are picking up stuff directly from post decon to then make wise decisions that someone needs to go back to make sure they're clean, other things like that. Not that you're just picking up from the actual event because it just has moved downwind from you. So that's the first important thing. But as far as the monitoring, kind of the stuff that we talked about is standing downwind, obviously, from that, because if you do have wind, you obviously a lot of these times they're going to be outside. You want to be sampling downwind, because if you're sampling upwind, you may not be able to collect that information into the detector with it. It's also safer for you as the operator to be standing upwind and being less exposed, especially if someone is off gassing and it could potentially be at levels that aren't safe for you. Obviously, you'll have protective equipment on, but you're just always wanting to try to minimize your exposure, because the suits can't work forever at high concentrations, especially from there. So what you want to do is hold it as close to the surface as possible, but do not touch, because if you touch, that could then transmit compounds or materials to the detector, and then you can get readings or alerts coming from that. So as close as possible, but not touching, and moving very slowly. You want to talk as far as some of the extremities, or if you know the person was exposed in a certain area and not in another, that's helpful to know, and that's where you want to concentrate on validation of the decon. Now, as well as if they were exposed, for example, on the top part of their body, and the decon process involved, we happen to be using water, for example, and then there's potential that it could have gone down to the lower extremes. You want to do that. If you're doing a hybrid decon process and we're more localizing for what that is, then you should be concentrating more so on the affected parts. But as a general rule, the extremities are important to be able to do that, as well as, for example, if you're dealing with organophosphates, for example, there's certain parts of the body that are more conducive for that to be transmitted into your body. So you can be concentrating on those as well to be able to do that. So slow and steady wins the race, not directly touching the thing, and moving slowly to correlate with the detection and the response time of your approach. And then, as Christina said, get them out there as soon as you can, but do it in a way that you are properly using your detectors so they can detect, so you're getting that confidence that you're doing it properly and that the person is properly decontaminated.
So these couple of slides I also shamelessly stole from First Line. So one of the things that we just wanted to remind you with before we break is that as we've gotten more science behind decon, we've been able to take things from the way we used to do business on the left-hand side of the screen and start doing things in a more efficient manner and farther forward. So for instance, the picture on the right is being done in a hallway on a different floor of a building. So if you were to have a lab or an event that was isolated to one apartment or one laboratory, instead of spreading that contamination outside of the building, you're better off to try to do a decon process right there as you exit that space and not spread it any further. And so the hybrid decon approach allows us to do that. But again, we have to be really careful and cognizant of the fact that we have to make sure we have removed the material and that we've detected to ensure that it's removed so we don't spread it further. The same type of thing occurs with the operational time. So where we used to spend hours sometimes getting things set up and getting ready, and oftentimes before we ever made an entry, remember that if there are individuals that are exposed, time matters. And so when we start thinking about the fact that somebody may have something on their skin, we have to get that off as quickly as we can. Now, if they have it in their lungs, even more important that we minimize that time that they're in that environment and get that out of their lungs. And so we really have a factor of 5 savings in time by going to a hybrid decon approach. And then, of course, there's the waste. Going from bladders of material that is being pumped off from the water. So I was saying overpacked drums, but reality is we had incidents where you had bladders full of material that is now contaminated waste and has to get treated accordingly. And switching now to where the absorbent materials get right in the bag with your waste PPE and just get thrown away as one bag of material. So drastic reduction there. So before we go, we'll go to questions next because I see a couple of questions up there. But I just want everybody to remember that detection and decon have to be treated as a system. So in order to be able to determine that your decon was successful, we have to be able to measure that. So you have to understand how they work together, and you have to understand their limitations. Like Scott was showing you earlier, when you're doing an organophosphate and you've used Dahlgren Decon for destruction, you need to wait a little bit before you measure that destruction to ensure that you've already oxidized the phosphoric acid that was in the Dahlgren Decon itself. Now that happens in a matter of a minute or so, and so it's right after it's mixed and used, you have to wait the little bit of time that they recommend for the destruction, and then you'll be confident that that's been taken care of. The approach you use for your decon, it's going to be based upon the material itself, the state of the material. So remember, gases, solids, liquids, aerosols all have different characteristics for decon. The chemistry of what's occurring and the chemistry of the decon solutions that we may use. The vapor density of the material. Remember, when we're talking about gas phase decon, those things with a higher vapor density are going to take longer to remove. And then, of course, there's other things that will come into play depending upon specific materials that we're looking at. Make sure you choose your decon location wisely. We need to validate that the decon has been confirmed, but we also need to make sure that we're not getting any interaction from any chemicals from the hot zone interfering with where we're measuring that the decon has occurred. And so, but we also don't want to bring any contamination potential into what would be our cold zone. And remember, detector sensitivity and response times do matter. These are things that we have to take into consideration to make sure that we're using an appropriate method for the detection on the clean end. And just because the individual has gone through the decon line doesn't necessarily mean that they are now clean or safe. We have to go forward and check them. Reality is, in many of the old brushing methods that we did, we actually spread more contamination than we did remove contamination. And that, once we started testing a lot of that, became eye-opening. And why that we've spent so many years now, since 2007, doing experiment after experiment on human skin and figuring out what are the best ways to decontaminate and how do we prove that we've done that. With that, I think I'm going to pull up and see what kind of questions we have first, and then see if anybody else has more questions. We'll go from there. So the other question, so one of the questions that Brian Hobbs had is, will sulfur-based agents show up on an H2S sensor? And so for that one, I am going to, well, it's going to depend upon which H2S sensor. So yes, there are some that SO2 does show up as a cross sensitivity. And so not all sulfur-based materials show up as a cross sensitivity, but there are many that do. Hopefully that answers your question. If you want to look at your specific sensor, your best bet is to go to the manufacturer's handouts, but you could also go into the ERDSS software and pull up the sensor that you have and see what other things it can detect. You see if there's any other, okay, let's see. We have Sean. Yes, blot, like club soda on a food spill to prevent a stain. Absolutely. Let me see if I can pull these things up. Okay. Will bleach cause a false positive initially like Dahlgren, as well as will bleach cause conjugates that won't cause the meter to go into alarm? So false positive like Dahlgren, no, unless the bleach contains a whitener that has a phosphorus-based material in there. And so some bleaches, yes, some bleaches, no. But most bleaches are a chlorinated material, and therefore you wouldn't see them on the AP4C. You may see them on other instruments though, because you do have that type of material. From Brent up in near Niagara, just to clarify, if water soluble greater than 10%, just straight water. Skin especially not to aid in its skin absorption. So yes, if it's water soluble already and you're using water on the skin, you can use water or soap and water. If it's not water soluble, that's where you need to use water as a physical removal process. So you're just using water to use the force to shear it off of the skin. By adding soap, you increase its permeability into the skin. So water soluble, you can use water or soap and water. Non-water soluble, use water only. Hopefully that makes sense. Amanda, where does soiled equipment go that needs to be reissued? Field detectors, weapons, etc. How do you clear those materials to give back to the users? Yeah, so this is one of the things where it gets interesting. You do have, we usually have an equipment drop in the decon lines. And that ends up being one of the areas where all of those detectors and all of your weapons and things sit until we can get back and do a very methodical decontamination on those to ensure that they're good to go. And I'll give you an example. Way back when we were doing some experiments and we were measuring sulfur mustard, so the real sulfur mustard, and we were measuring it with the original Ahura, so a Raman system. And with that, deconned everything, did all the wipe downs, everything we were supposed to do. Everything looked good. We weren't getting any measurements for anything we had. Put it in the box, sealed the box, transported it back to where it was going. And all of a sudden we have sulfur mustard fumes in that box. What had happened was the sulfur mustard interacted with the O-ring that was in the sensor. And that's why most people have gone away from silicon-based O-rings, because silicon absorbs a lot of these materials. And so that was like an oh wow for us at that point, because if you have silicon-based O-rings and things, you have to replace those on the soiled equipment before you can put it back into service. So reality is, most of your equipment, you're going to have to go through and monitor it and make sure that it is now clean. The good news is most of the equipment that we bring down range is gas-based. And so most of the cases, gas goes on it, gas comes off it. Do take extra care when you're bringing instruments down range that require you to set them down, that you bring a piece of plastic or something with you to set them on top of, to ensure that you're not cross-contaminating anything. And then what does the LOD of a detector need to get to be a good candidate for the effectiveness of decon? Well, that's going to depend upon the chemical itself. And in this case, what we need to do is get below the permissible exposure limit of the material. So if there is a published permissible exposure limit, we always want to make sure we can measure below that and in a fast way. So if the sensor takes a long time to read when at low levels, then it might not be the perfect one for post-decon. It might be suitable for pre-decon or for downrange. And so it's going to be all about getting as low as you can below the permissible exposure limit. Once we get below there, we don't really care, right? We can be in that for an 8-hour workday and be pretty good. And so that's where we go with that one. Hopefully, Amanda, that answers your question there. Scott, is there anything you want to add to any of those?
No, I think the point of understanding what, it'll vary by the material. So one of the challenges you will face, to be blunt, is if you're dealing with, God forbid we have to deal with A series or a V series agent, I mean, because your concentration level is parts per trillion, it's going to be really hard to validate, any decon method. You can't be 100% certain that you don't have, nanograms or picograms of material there, which then could still be helpful. So in those cases, you probably are going to have to dispose of the detector with it, but a lot of the other materials, you should be easily able to detect it, but the driver is always the permissible exposure limits of those materials.
Absolutely. Even though we have lots of detectors and things that can measure low levels of sarin, VX, A series, when it gets to being able to detect them post-decon, or where we can detect them at well below what would be considered an operationally relevant level or below permissible exposure limits, we don't have anything that detects that low for a lot of the warfare agents. Okay, we can detect them below ideal H, but we can't get them usually below permissible exposure limits because those permissible exposure limits are so low. We're talking parts per trillion for some of them, and then parts per billion. And so there's nothing we can do at this point in time for post-decon unless you want to take a sample to a lab and confirm. And in that case, you can pre-concentrate samples, take them to a laboratory, and do an analysis. This is something where even some of the CSTs with their mobile laboratory, for those in the US, sorry, our civil support teams, National Guard, we have them in every state, at least one, and they have mobile laboratories that have a really nice GC mass spec in them. And so in that case, if they can pre-concentrate the sample, they may be able to measure post-decon and tell you, confirm that you've done it. But again, that decon, that run's going to take a minimum of 15 minutes. And so you're going to have to be out of your gear, but your PPE and your equipment may be able to stay. Okay, are there any more questions? As always, Scott and my email addresses and phone numbers are up above. You can contact us at any time with questions if you would like. And you'll also receive an email following up from Proengin, which will send you a link to the webinar. So we recorded everything, and we want to make sure that you can go through these on your time. And a lot of you, I know it was late at night or early in the morning, and you might want to go through it a little bit slower. So, Scott, anything else from you?
Just if some people want continuing education credits as part of this, you can reach out and we can help you with a certificate as well for that, if that's of something of interest to you.
I forgot about that one. Thank you.
Sure.
Okay, folks, stay safe out there. Have a wonderful day, and let us know what we can do to assist. For any of you that are interested in the drug topic, I'll be doing a webinar next week on Wednesday on the drugs. And then the following week, I'll be doing one on the new Explore IR gas phase infrared, which is very cool too. So all of these things together form our toolbox, and without that toolbox, we can't get anywhere.
Yeah, and just one additional thing, if there are topics of interest that you guys out there think would be helpful, it's always helpful for us to know what those are, and we always try to gear our educational series to benefit the industry and people that are out there every day dealing with these environments. So anything you can to help us, we try to be responsive to that.
Perfect. And Zach, I will be putting up information on the next webinars on my Facebook page. So Christina Baxter on Facebook, and I'll have those up there and on LinkedIn. If not, you have my email from these invites, and just go ahead and email me and I'll send you direct links. Chris, it won't be on the TIPS website because I never get around to updating it. So, but the webinars will be available, and we use them on the, there's a Proengin closed YouTube channel that we'll put them on. And then it'll send you a link to that. Okay, thank you guys. Have a great day, and I'm off to the airport. So I will talk to many of you next week, and stay safe. Keep up the good fight. Thank you.